Today on the Perception and Action podcast, what are the limitations of current VR and brain training technologies that use an isolated, process-driven approach to improve perception and decision-making in athletes? How can these be improved by following the principles of ecological dynamics? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception and Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In today's episode, I want to look at a couple recent articles published by Keith Davids and colleagues in which an ecological dynamics approach is used to analyze some of the hot new technologies that are being developed for training perceptual and cognitive abilities in sports. The first article I want to look at is one published by Ian Renshaw and colleagues in Frontiers in Psychology. As the authors begin by noting, quote, there has been a recent upsurge in the process training industry, proposing how to improve isolated processes such as perceptual and cognitive capacities like vision, attention, creative thinking, memory, ultra-fast decision-making, in order to improve performance at work, in tests and examination, and in sport. In a related vein, a brain training industry also promotes the idea that, for example, playing digital games not only makes you better at playing the games, but also makes you smarter, more alert, and helps you learn faster. End quote. Of course, here we're talking about products like NeuroTracker, the Spark Sensory Station, FitLight, Striver, and so on. As Renshaw and colleagues also point out, there are some key reasons these technologies keep appearing. First, they fit nicely with the idea of the importance of marginal gains or targeting 1% improvement in sports. Because athletes can only spend so much time on on-field training, doing off-field training with these technologies would seem to be a great way to give them an edge. Second, of course, is the financial incentive, as sports training technologies is a multi-billion-dollar industry. But as I've lamented several times on the podcast now, these technologies have moved ahead despite very little evidence that they can really improve perceptual cognitive abilities and brain processes in a way that is transferable to real-world sports performance. In their article, Renshaw and colleagues identify several limitations with these types of products from an ecological dynamics perspective. So, I think going through these papers is not only valuable as a cautionary tale about the use of these technologies, but it also serves as a way to strengthen our understanding of the key principles of ecological dynamics. So let's have a look. First off, it's important to emphasize that most of these training technologies for improving the perceptual cognitive abilities of athletes adopt a modularized or process-driven approach. That is, they assume that isolated processes or modules in the brain, like visual acuity, attention, and decision-making, can be trained separately from performing the action in context. It is further assumed that after training, these enhanced processes can be put back in the whole perception action system, leading to transfer of training to performance on the field. These basic assumptions are not consistent with the ecological dynamics approach, which considers perceptual, cognitive, and action subsystems to be deeply linked in their activity, functioning as continuously integrated and highly coupled systems. Quote, theoretically, it is not coherent and of little value to use a modularized approach and decouple processes of perception, cognition, and action to train them in isolation. Further, ecological dynamics is deeply concerned with knowledge and considers intentions and cognition to play an important role in theoretical explanations of human behavior. End quote. Another fundamental difference between the process approach used by many sports training technologies and ecological dynamics is that most of the former systems are based on indirect methods that build knowledge about the environment. That is, knowledge that can be used to describe, either verbally or using an illustration, performance. For example, describing the position of players in a particular defensive alignment by drawing it on a whiteboard. Conversely, ecological dynamics argues that athletes need to develop direct knowledge of the environment. Quote, in contrast, the more direct knowledge of the environment supports how an individual interacts with the performance environment, intentionally, perceptually, and motorically, in picking up and utilizing affordances from the performance environment. Gibson proposed that knowledge of the environment is expressed by action and implies direct perception and direct experiences with specific environments. Adaptive behavior emerges as a continuous cycle where performers can prospectively control their actions by detecting information. Consequently, ecological psychologists suggest that direct learning to develop knowledge of the environment is achieved by doing. End quote. Another limitation of most perceptual training programs for sport that Renshaw and colleagues identify is that most adopt a one-size-fits-all approach. In most of these programs, the information used to anticipate and act in research studies is thought to be commonly used by all sports performers, regardless of skill level. An interesting example of this that they discuss is one that rarely receives much criticism: quiet eye training. The central premise of quiet eye training is the search for an optimal behavior. That is, training a performer to adopt a quiet eye fixation period of a particular duration. However, evidence is emerging that variability in gaze patterns in learning and performance are task and individual specific, as are many movement behaviors. According to Renshaw and colleagues, this observation highlights the fallacy of attempting to replicate a universal optimal gaze pattern to sit alongside an optimal universal movement pattern. What is the evidence to support the indirect process-based approach so popular in the sports training industry now? In a systematic review by Harris and colleagues published in 2018, 43 studies purporting to examine the beneficial effects of the use of a commercial cognitive training device on sports performance were identified. Their search yielded only a single study that examined the most important issue of transfer to real sports performance. Unsurprisingly, they concluded that there was limited evidence for positive transfer of training to sports. I reached a very similar conclusion in a book chapter I have coming out later this year. Instead of looking specifically at commercially available devices, I examined all the published studies I could find that have measured some type of transfer using perceptual cognitive training for sport. Of the 22 studies I looked at, only 2 measured FAR transfer and used appropriate controls so that the training effects could be interpreted. I've included a link to the summary table of the studies in the show notes. The vast majority of the studies in this area have only measured near transfer, showing that participants improve on the task they were trained in or a very similar one. Both Harris and colleagues and I concluded that the lack of evidence in support of perceptual cognitive training for sport is primarily due to the fact that these studies of FAR transfer have just not been done. But Renshaw et al. Challenged this idea in their recent paper. Quote, "There are 2 problems with this conclusion. First, it does not take into account that there may be many studies of perceptual cognitive process training which have not been submitted for publication because researchers did not find the expected benefits. This is a limitation that quantitative reviews always need to acknowledge, known as publication bias. Second, it is possible that the lack of beneficial effects may be compounded by a lack of a substantive theoretical rationale implemented in research designs for how process training may yield benefits to performers." End quote. In summary, the bulk of research evidence suggests that training on these technologies only improves performance for the practice task, or nearly identical ones, and does not greatly enhance other related skills. That is, near, not far transfer. To finish their article, Renshaw and colleagues raise a couple of key questions that need to be asked about process-driven perceptual cognitive training programs in sports. First, how can relevant contextual information be distinguished from irrelevant information before the detected information is transmitted to the brain, as proposed in theories emphasizing the role of perceptual cognitive processes? This is an important question because explanations of brain training effects rely traditionally on the assumption that brain processes detect, attend to, learn, or memorize relevant information. Information from a sport context will then feed neural networks, allowing brain structures to organize or program a motor response. But how are brain training games designed to distinguish distracting informational sources in competition from those which are simply raising alertness for each individual? Second, how do skilled performers adapt and vary brainwave parameters during performance to support coordination of their actions with important environmental events, objects, surfaces, and significant others? Rather than looking for optimal values of brain waves or quiet eye durations, Renshaw and colleagues propose that it would be more important to look for critical threshold bandwidths, which could be functionally distinctive according to task and individual constraints, within and between expertise levels, while studying emergent actions in sport performance. The second article I want to look at is one currently impressed by Stone and colleagues, specifically focusing on the use of virtual reality or VR in sports training. Again, they emphasize that despite the number of sports organizations investing in VR systems, there is currently limited scientific evidence to inform and underpin its application. More importantly, and similar to what I've already discussed, it's unclear whether VR systems develop skills and expertise beyond the specific practice context in which they're implemented, and how the effectiveness of VR compares to other methods of learning and training. While there may be some benefits for athletes, a judgment needs to be made as to whether VR systems are worth the time, money, and effort involved in their implementation. As first discussed by Kathy Craig, VR has the potential advantage over other types of perceptual cognitive training in that it could allow athletes to become attuned to specifying information sources in an environment in which the information is coupled to the action possibilities. Quote from the Stone et al. Article, "Gaining this intertwined relationship between subsystems of action, cognition, and perception, which supports interactions within a performance environment, is the fundamental basis for using technologies like VR systems to enrich athlete learning and performance. Interacting constraints designed into a representative simulation of a performance environment provide a framework for the acquisition of functional, goal-directed behaviors in learners. This conceptualization from Ecological Dynamics provides a clear rationale for understanding how task and environmental constraints designed in VR environments could guide each individual performer's interaction and learning possibilities." End quote. As I've argued in some of my recent articles and chapters, VR developers should not be looking for one optimal pattern of coordination towards which all learners should aspire, but instead, training should be concerned with manipulating constraints to support self-organization. A standard one-size-fits-all practice schedule could be avoided by using VR systems to individualize task and environmental constraints. And as I've also discussed, designing these constraints within the VR system needs to closely follow the principles of representative learning design, which has two critical components: the functionality of perceptual information and action fidelity. In terms of perceptual information, VR systems have a distinct advantage in that they can recreate an egocentric viewpoint of the environment rather than a fixed allocentric one. Researchers have previously demonstrated that participants make faster and more accurate decisions when they're presented with a viewpoint from their own personal perspective, the egocentric viewpoint, compared to viewing a live broadcast, an allocentric viewpoint. In terms of action fidelity, it is critical that within the VR system, the performer is able to reorganize their motor system degrees of freedom in practice in the same way as they would be required to in competitive performance. This idea questions the usefulness of VR responses like finger movements on a digital controlling system, the use of wands or hands or verbal responses to simulate action. It also challenges the effectiveness of quote-unquote immersive systems that are not truly interactive, like Striver and NeuroTracker. Quote, "Despite action fidelity being a critical component of VR design, importantly, it is not only the ability of VR systems to enable representative movement responses, but also the ability of participants to directly interact with and shape these environments through their movements. Learning is founded on continuous interactions of a learner with a performance environment in successful sports practice programs. Current VR designs which limit interactive movements of learners can be circumvented by using immersive technology that affords the capacity for individuals to navigate through an ever-changing environment and reorganize actions relative to information available in the virtual environment." To finish the article, Stone and colleagues highlight some of the potential advantages of VR to supplement and enrich current training programs. Specifically, by careful manipulation of constraints to enable 1. Individualized training and assessment, 2. The development of variability and creativity in interacting with the affordance landscape, and 3. Enhancing context-dependent decision-making in representative performance conditions. Quote, "The essential element for VR design here is to ensure availability of a landscape of affordances, which promotes what Bernstein called repetition without repetition, to enhance dexterity, problem-solving, and exploratory behaviors of athletes as performers seek to solve problems and make decisions across subtly different scenarios. From this theoretical rationale, it is argued that subtle variations in VR practice environments will promote the necessary flexibility in performance through continued exploration and self-organization of action responses as the performer adapts to these changing constraints. Through this continued exploration of their environment, performers will be encouraged to interact and discover different movement solutions to reach the same outcome. That is, system degeneracy." End quote. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including an extra monthly episode and written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled.